I would like to demonstrate why ballistic pendulums cannot produce quantities of heat. We will use a common ballistic pendulum that has been available to us on the internet with a bullet mass of 10 grams, a block and bullet combination mass of 2,000 grams, and it has the ability to rise 1 meter after the bullet strikes the block. This will give us two variables of the law of conservation of momentum formula. We can find the third variable, V2, by plugging in an arrangement from the distance formula. This is the distance formula with the height and the acceleration of gravity. Pendulum would look something like this, with the 10-gram bullet striking the 1,990 gram block, giving us a 2,000 gram block and bullet combination for a height of h. This is the momentum formula. Since we know the mass of the bullet and the mass of the block and bullet, it would be convenient to put them both on one side. We can do this by dividing both sides of the equation by m2, mass of the block and bullet. That places the m2 as a denominator on the left. We can do the same for v1 and place it as a denominator on the right. Now this is still the law of conservation of linear momentum formula, with all the mass on one side and the velocities on the other side. Now we know two of these, we need to find out this one. V2 equals 2 times the height of rise times the acceleration of gravity. Plugging in our numbers, we get 1 meter rise. We get a velocity of 4.429 meters per second for the block as the block is being struck by the bullet. So plugging our numbers into the law of conservation of momentum, 10 over 2,000 equals 4.429 meters per second divided by V1. So we can determine V1 by switching this to the other side and multiplying, and we get 885.9 meters per second for the velocity of the bullet. We can check this by plugging it into the same formula, law of conservation of momentum, and see if it comes out correctly. Now I did not round this to 10 meters per second. That was done on the other video that's available on the internet, on YouTube. But I left it as 9.81 meters per second for the gravitational acceleration. Now with these two numbers we can determine the kinetic energy of the bullet, and we can determine the kinetic energy of the block and bullet after it combines. Using the law of conservation of, using the kinetic energy formula, we can determine the kinetic energy of the bullet and the block. We'll first do the block. The block weighs 2,000 grams or 2 kilograms. This has to be changed to kilograms because the formula is arranged that way. And the meters per second is squared, and we come out with 19.62 joules of energy for the block and bullet combination after it has been struck, after the block has been struck by the bullet. For the kinetic energy of the bullet, we have to multiply 1/2 by 1/100th of a kilogram, that'd be 10 grams, by that velocity. 885, I just left those numbers in because my calculator doesn't care. And we get 3,924 joules for the kinetic energy of the bullet before it strikes the block. So after the bullet strikes, we get 19.62, and before that, we got 3,924. So that is what's left over, and this is what was the original. So if we subtract what was the original, or subtract what is left over from the original, we get a whole lot of loss. From V1 to V2, we have a loss of 3,904 joules. 3,924 minus 1962.62 is around 3,904 joules. So you divide the 3,904 joules by 3,924 joules, and you get a 99.5% loss. Now that's a huge amount of loss. In and of itself would make you question, I would think, the formula. But we will go on and we will actually prove it, not just question it. Now, interesting enough, the M1 over M2 will tell us the quantity of energy that is saved. In this situation, it was 10 over 2,000, which would be 1 over 200. Only 1/200th of the energy of this system was saved. The rest was lost. Now we know that motion is a form of energy, and we also know that heat is a form of energy. And they propose that motion is lost as a form of heat, so they agree. But we can also use the same terminology for one and the other. We can say that motion is lost just as accurately as we can say heat is lost. So kinetic energy says that 99.5% of the motion is lost because motion and heat are both forms of energy. Now momentum says that there is no motion lost. None. You have the same amount of momentum on one side as you do on the other. There is no momentum lost. So one says just about everything is lost. The other one says nothing is lost as far as motion. Now we're going to check this out by doing an experiment. And the experiment is very similar to the Dawn mission experiment that NASA conducted. Now they did not conduct this as an experiment. They were stopping the spin of the satellite so that it could launch the satellite into orbit. But you can find this on the internet. It's quite interesting. But the Dawn mission yo-yo to spin device stopped a 1,420 kilogram satellite from spinning by using 3 kilogram masses on the end of cables. Now, if 99.5% of the motion is lost to heat, the 3 kilograms could not restore the motion if they were left attached. Now you can leave after the 3 kilogram objects spin out on the end of the cables, they are released. And by them spinning out on the end of the cable stops the spinning, and then they release the cables with the masses. If the cables of the 3 kilogram were left attached, the original spin would be restored to the 1,420 kilograms. That seems like common sense to be able to say that. But the cables would restart the respin of the satellite, but they do it in the opposite direction. So they will stop, say, a clockwise direction and then spin it in its counterclockwise direction. By accident, NASA had a 3 RPM backspin from an original forward spin of 46 RPM. That's about 6.5%. This was an accidental, I think anyway, an accidental respin by miscalculation, and before they released the satellite cables, the cables to the 3 kilograms. So their backspin was actually more than the motion available to them according to their predictions. If the 3 kilograms had conserved energy in the fully unwound position, they would only be moving about 20 meters per second. If I remember correctly, that's less than what a high school baseball player can throw a baseball. That's pretty slow. This would be only about 5% of the motion needed to restart the spin of the satellite. And they've already shown that there is more than that available, because this was just an accidental backspin. Momentum conservation says that the 3 kilograms would be moving 400 meters per second for the unwound position at the release point. And they would be fully capable of restoring the satellite if they were left attached. This can be proven with experiments that you can conduct in the lab. They don't have the mass ratios, but they have enough mass ratio to, the mass ratio of this is about 400 to 1. The mass ratio of these is about 20, 30, sometimes 15, sometimes only 4 times as much. But these spheres can restart the cylinder. The cylinder will be restarted when the spheres reach the maximum point, are left attached, and rewrap. And you can see these on the internet as well. But these experiments that mimic the Dawn mission experiment prove that large quantities of heat are not lost in these type of interactions. A small object given its motion to a large object given the motion back. Heat is not lost, motion is not lost. That is proven by these experiments.